In this module, we're discussing the process of factoring polynomials. And in the first topic, we're discussing two factoring techniques. One of them is factoring out the GCF, the greatest common factor, and the other one is factor by grouping. Okay, before we can get to these two specific techniques, we need to actually define and understand what it means to factor a polynomial. Okay, so the first definition says to factor a polynomial is to write the polynomial as a product of two or more other polynomials. So for example, if you take the polynomial x squared minus 9 and you think about it long enough, you might see that you can rewrite this polynomial as x minus 3, x plus 3. So this process of going from x squared minus 9 to the product x minus 3 times x plus 3, that's called factoring. Another use of the word factor comes from trying to describe each of the quantities in this product here. Okay. So each quantity in the product x minus 3 times x plus 3 is called a factor. Okay, so x minus 3 is a factor here, and x plus 3 is also a factor here. So the polynomials being multiplied together are each called factors. So unfortunately, not all polynomials can be factored. Okay, and when a polynomial cannot be factored, it's called a prime polynomial. Right, so we'll see some examples of prime polynomials as we work through the module. But if you cannot factor a polynomial, it's called prime. So hopefully factoring is not an entirely new idea to you. Okay? If you think about it, you've been exposed to factoring before. Right? For example, if I tell you to factor 21, you would write it as a product of 7 times 3. Right? This is sort of what we do with factor trees. A factor tree breaks 21 into its two factors. Okay. So factoring is a process that you've been through with regular numbers. Now we're just applying this same process to polynomials. Okay. When you factor numbers, like when you factor 21, you go through and you think, okay, what two numbers can I multiply out to get 21? You're going to have a similar process when you're factoring polynomials. Okay. When you're factoring a polynomial, you have to think, which two other polynomials can I multiply to get to the original polynomial back? Let's look at an example. So the question is, how do we factor polynomials? Okay, how do we take a polynomial and break it down into a product of other polynomials? And the answer is you have to be really good at multiplying polynomials. If you understand completely how multiplying polynomials works, then you can factor polynomials very easily because factoring is simply going backward. Right? So if, for example, you're given the problem multiply 4x times 3x plus 5, then you would distribute and you would get 12x squared plus 20x. Now, if on another piece of paper I give you the problem factor 12x squared plus 20x, how are you going to do that? Well, you're going to say, I know if I multiply 4x times 3x plus 5, I get 12x squared plus 20x. So basically what you're doing is you're reverse distributing. Okay, you're thinking about what could I multiply by to get 12x squared plus 20x. Okay, factoring is the opposite of multiplying. It's the reverse of multiplying. Hopefully by now I have pounded into your head that factoring is the reverse of multiplying. Okay, if you need to factor a polynomial, you have to think of two polynomials that you can multiply together to get the original polynomial. But even if you understand that general concept, you may have no idea how to actually do a factoring problem. Okay, so what we're going to continue on and talk about now are two factoring methods that you can use to help break a polynomial into a product. The first one is called factoring out the GCF. The second one is called factor by grouping. Okay. So we're going to talk about the background for these two procedures, and then we'll outline the procedures, and then we'll do some practice problems. Alright, so if we want to be able to factor out the GCF, we have to talk about the definition of the greatest common factor. So the greatest common factor between a list of integers is the largest factor that those integers all have in common. Okay, so for example, you can find the GCF between 42 and 36. Okay, to find the GCF between 42 and 36, you would have to factor the numbers down completely. And the GCF is the greatest factor that the two numbers have in common. So for example, 42 is 2 times 3 times 7, and 36 is 2 times 2 times 3 times 3. So they have in common this factor of 2 times 3. Okay, so the GCF is exactly how it's named. It's the greatest common factor. If you want to find a GCF, you factor your numbers and look for the overlap, look for the common factors. Now this idea extends to variables. Okay, so for example, we can find the GCF between x to the 4th and x to the 7th. We would do that by writing out exactly what x to the 7th is and writing out exactly what x to the 4th is and looking for the overlap. So you see, both x to the 7th and x to the 4th have an x to the 4th in common. So the GCF is x to the 4th. In general, the GCF between x to an exponent and x to another exponent is going to be x to the smaller exponent. Okay? So x to the 4th and x to the 7th have x to the 4th in common because the 4 is the smaller exponent. Alright, so let's move on. So example 1 asks us to find the GCF for the list of terms. So this isn't actually a factoring problem. This is sort of preliminary to factoring. This is trying to make sure you understand what the GCF is and how to find it. Okay, so let's look at our three terms here. We have 25p to the 5th r to the 7th, 30p to the 7th r to the 8th, and 50p to the 5th r to the 3rd. So what I'm going to suggest is that you treat the coefficients in each variable separately. Okay. So first let's find the GCF between 25, 30, and 50. Okay. After that we can go on and talk about the p to the 5th and the p to the 7th and the other p to the 5th and then the r to the 7th, r to the 8th, and r to the 3rd. Okay. For these three numbers we're going to need to factor them down so we can find which factors they have in common. So let's do that quickly. So here's the result of factoring down my coefficients. 25 is 5 times 5, that's it. 30 is 5 times 6, but then the 6 breaks down to 2 times 3, so 30 is 2 times 3 times 5. And 50 is 5 times 5 times 2. So if we're looking for the GCF between these three coefficients, we find the largest factor that overlaps all three of them. Okay, and the only thing that all three have in common is a single 5. Right, this 50 has a 2 in it, but 25 doesn't have a 2 in it, so that can't be part of the GCF. And 30 has a 3 in it, but 25 and 50 don't have a 3 in it. Okay, so for the three numbers, the GCF is 5. Okay, so when we start building our GCF for these three terms up here, we know we're going to have a 5 as our coefficient. Okay. But now we need to go in and focus on the variables. P to the 5th, P to the 7th, P to the 5th. Okay, so what's the GCF between those three variables? Remember, when you're looking for the GCF between a variable to an exponent, you should take the smallest exponent. Okay, between p to the 5th, p to the 7th, and p to the 5th, they all have 5 p's in them. Okay. All right, so using that logic of taking the smallest exponent, we know that our GCF must have a p to the fifth. Similarly, when we look at the r variable, we have an r to the seventh, an r to the eighth, and an r to the third. We need to take the smallest exponent in this case as well. So r to the seventh, r to the eighth, r to the third, they all have an r to the third in common. Okay, this means that our GCF overall is 5p to the fifth, r to the third.